Alright, this is section 2.2 where we talk about introduce a new topic called the limit. So we first talk about a function x minus 1 over x squared minus 1. If you factor the denominator, you see that the numerator and denominator have a common factor that you can cancel, and you're left with this guy here. Now, they say in the book, and they're correct, they say that this guy equals this guy except when this one is not defined at negative 1, but this one's also not defined at positive 1. So you can take the limit of this guy as long as you remember that it's not defined at 1 or negative 1. So if you were to graph this thing just at the portion where you're approaching 1, you actually have a hole there because this original function is not defined at 1. Even though this is 1/2, this is the original function that you started with. And even if you do these reductions, you have to consider the original function that you started with when you take the limit. So if you approach 1 from the left or from the right, you see that you keep getting closer and closer to 1/2, 0.5. Here you get closer and closer to 1/2, and here you get closer and closer to 1/2. Alright, so what we can say is as x approaches 1, comes in here to 1, f of x approaches 0.5 or 1/2. So the way we phrase that is we say the limit as x approaches 1 of x minus 1 over x squared minus 1 equals 1/2. So here's our definition of a limit. This SP is an abbreviation mathematically which means suppose. Suppose f of x is defined on some open interval that contains a, except possibly at a itself. Then we write the limit as x approaches a of f of x equals L. Alright? If we can make the values of f arbitrarily close to L, as close as we like, by restricting x to be sufficiently close to a, but not equal to a. We do not care what actually happens at a. We just care that as we approach from the left and right that we approach the same number. So the value of f approaches L as x approaches a, or f approaches L as x approaches a. Now note, one of the more important parts of that definition is that it's x is not equal to a. This means we never consider x equals a. F of x need not be defined when x equals a. The only thing that matters is how f is defined near a. So we don't care what happens at a. So let's look at figure 2 in the textbook. All three of these are functions where the limit exists. All three have the same, or have a different situation, but with all three of these, the limit as x approaches a of f of x equals L, and all of these have that same limit that does exist. As you approach from the left and the right, you approach the y value of L, and at a, it's defined as L. F of a equals L. Now here, you approach from the left and you approach from the right, and you approach the y value of L. But here, a is not, f of a is not defined. There's a hole there. And then here's the third case. If you approach from the left and approach from the right, you approach the y value of L. But notice a is defined, but it's not defined there. It's defined down here. So again, whether you have a defined at L or not, it doesn't matter. All we care about is as we're approaching it from the left and the right. So if we look at example 1, they give you this function here, and you plug in these values as you get closer and closer to 0, plus and minus for each one of these. And you can do it that way because this function is t squared, so whether it's positive or negative when you square it, it becomes positive again. So you're going to get the same y coordinate for all of these. Okay, and then what you see here as t gets smaller and smaller and closer to 0, you get this guy is closer and closer to 0.1666666 with a whole bunch of sixes, which turns out to be the fraction 1/6. And that's what our guess is. Now if we were to continue this calculation with even smaller numbers, watch what happens. We get, here we got 5 6s with a 7. Now we're only getting 3 6s with 7. Now we're only get 1/6 of the 7, and now we're not getting any number at all, which we know is not correct. We should be getting some answer. And what's happening here is you're using such incredibly small numbers that your calculator can't handle it, and it's giving you misleading data. If you were to look at it from -5 to 5, it looks like this, and you can see that it approaches 0.166. Between 0.10 and 0.20 is 0.16. Here, if you go from 0.1 negative and positive, it approaches that number. Okay, and now if you go -10 to the -6 and 10 to the -6, these are 1 millionth and -1 millionth and +1 millionth. It's all over the place. And then when you go to 10 to the -7, it jumps up even more. And that's because even if you were to graph this like the author did on a computer, your data is off when you get incredibly close to the number. So there's a certain point where you can't rely on your calculator anymore. Alright, so let's look at example 2. They ask you to guess the value of the limit of sine x over x as x approaches 0. Well, you know it's not defined at 0 because you'd be dividing by 0 there, and that's undefined. But when you check this, you want to be in radian mode. Okay, and so we're going to pick numbers that are getting smaller and smaller and smaller. Right? And our y values get closer and closer to 1. And so our guess is that this limit does approach 1. And if you look at the graph, it's not defined at the point, but it is approaching from the left and right at 1. And so that limit does exist, and it is 1. Now example 3, they give you this guy. And first, just intuitively try and ask yourself, what's this guy going to equal? Well, as x gets closer to 0, this guy becomes nothing, meaningless. And as x gets closer to 0, cosine becomes 1, and the 10,000 stays the way it is. So this should approach 1 over 10,000. And so if you plug in numbers smaller and smaller and smaller, closer to 0, look what you get. You get 0.0001, which is 1 over 10,000. So our guess is a correct one. Alright, let's talk about the heaviside function. This is a function that describes the current in an electric current that switches on at time 0. So at any number x or t less than 0, it gives you a 0 value. So any number in the negative area is always 0, 0, 0. As soon as you hit 0 or greater, it flips up and becomes 1 immediately. Right, this is describing an electrical current going through a wire or something like that. So if you looked at this guy, you would see from the left you approach 0, from the right you approach 1, so you would say the limit does not exist. But from the left, as t approaches 0, negative, if you put that little negative on the upper right of a number, that means you're approaching it from the left, from a lesser value. We can say that h of t approaches 0, and the limit as t approaches 0 from the left equals 0. And same thing for the right. From the right, if we put a little plus sign above and to the right of any number, that means you're approaching it from the right, numbers that are greater than 0. And we can say that h of t approaches 1 as t approaches 0 from the right, so we can now say the limit as t approaches 0 from the right of h of t equals 1. These are what are called one-sided limits. So here's your left-sided limit, left-hand limit. As x approaches a negative, you can say the left-hand limit of f as x approaches a is equal to L. If we can make the values of f arbitrarily close to L by restricting x sufficiently close to a, with x has to be less than a. For left hand, you're always saying that the value you're approaching is coming at it from the left, so it's less than. And the same thing is true for the right, except you just say greater than. Now these definitions are just like the definition on the first page, except you're restricting to less than or greater than. And so we say x is approaching 5 negative. That means we consider numbers only less than x less than 5, such as 4.9, 4.99, 4.999, and so on. X approaches 5 plus. That means we consider only x values greater than 5, such as 5.1, 5.01, 5.001. So definition 2 differs from definition 1 only in the way that we restrict x to be less than or greater than a. So now we can say our limit equals L if, and only if, the left-hand limit equals L and the right-hand limit equals L. And that's how you can prove something, a limit exists, is if you can prove the left-hand and the right-hand limit exist and they equal the same value, L. So let's look at some cases here. This one, these first three, A, B, and C, ask you to come at 2 from the left, come at 2 from the right, and then they ask you, does the limit exist at 2? So from the left, you can see you're approaching a y value of 3. From the right, you're approaching a y value of 1. So this one is 3, that one is 1. And so the limit does not exist because these two guys are not the same, equal to the same value. Now 5 from the left, 5 from the right, and then 5 itself. 5 is here. From the left, it's approaching 2. From the right, it's approaching 2. And so the limit of, as x approaches 5, equals 2. Now notice it's not defined at 5, and we don't care that it's not defined at 5 for 2. It actually, f of 5 equals 1, or something a little bit greater than 1. So even though the function is defined at 5 and it's not equal to the point that the left and right hand limit approach, we don't care. We only care about what's happening as we approach from the left and approach from the right. We don't care what happens at the point. Now if we look at something like this, this is a classic example of a function that just goes, the closer and closer you get to 0, the faster it goes up and down. Almost looks like an earthquake meter going off. This one, limit does not exist because as you get closer and closer to 0, your y values are all over the place. So it does not approach any one value at all. It doesn't even come close. Okay, now example 6 talks about something that we're going to call an infinite limit. Now we say it's an infinite limit even though the limit, it's not technically a limit, and an infinite limit does not, the limit does not exist, but we can still call it an infinite limit. Alright, so if we look at this guy here and see what happens, as we get closer and closer to 0, this guy explodes off to infinity. Same thing here, this guy explodes to infinity. So as you pick numbers that get closer and closer to 0, your function value get closer and closer to huge numbers, huge positive numbers. So we can say the limit equals infinity because we can get as close as we want to 0 and this thing will just explode. Alright. Now this does not mean that we regard infinity as a number, nor does it mean that the limit exists. It just simply expresses the particular way in which the limit does not exist. The limit does not exist, but it is an infinite limit. I know that's kind of confusing, but there you go. Alright. So the intuitive definition of an infinite limit is that the function is defined on both sides of a except possibly at a itself. We don't care what happens at a. So that the limit equals infinity as the values of f can be made arbitrarily large by taking x values close to a, but not equal to a. So another notation you can write is the limit as x approaches a of f of x equals infinity. You can also say f approaches infinity as a approaches x approaches a. And these are the other different ways that you can describe that. And so here you've got the same idea right here, and this x equals a is a vertical asymptote that is found by places where your function is undefined.